two concepts that I see as related are the no cloning theorem
Yes.
and computational irreducibility. So this is something popularized by Wolfram,
Yeah.
which I know you know, so I'll get you to explain it to the audience. But the no cloning may have implications that such a machine can't exist because it can't be a perfect copy of you.
Yeah. Okay. So by the way, no cloning and computational irreducibility are two totally different things. You know, we can talk about both of them. Okay. But the no cloning theorem is just a very, very basic fact about quantum mechanics. Okay. And it says that there is no physical operation that you can do that takes as input an arbitrary quantum state, you know, an unknown quantum state, like let's say a qubit, you know, a quantum bit, a superposition of a, you know, a 0 and a 1, okay, and that produces as output two identical copies of that state. Okay, so there is no quantum Xerox machine that is possible. Right, the ability to make perfect copies of things. This is fundamentally, you know, a classical phenomenon. Right, it is not true quantumly.
I'm sorry to interrupt. I'm sure you've heard of Leibniz's law of indiscernibles.
Yeah. Yeah.
Okay. So this isn't that.
No.
This isn't saying
No.
like, look.
This is a fact about physics, you know, that could have been false, right? But, you know, it is true because, you know, for a century, every experiment has, you know, told us that quantum mechanics is true. And, you know, as long as quantum mechanics remains the basis of physics, then, you know, then this is true. But it's not something that is a priori knowable. Okay, and so the sense of copying that I mean is copying the information. Okay, so think about classical bits, right? We all know that classical bits can be copied, right? If you have, you know, this has been the bane of the music industry and the software industry.
Right.
You know, if you have a file, right, you can make a copy of that file, right? You know, it won't be, you know, it'll have a different physical representation, you know, somewhere else in your computer's memory or in a different computer's memory, you know, but it will encode the same bits of information.
Okay. So Napster exists because the no cloning theorem is purely quantum?
Precisely. Yeah. So classical information can be copied. Okay, but what we're saying is that in quantum mechanics, you know, even the information cannot be copied. Okay, so quantum, we have to take a step back and say, you know, what is quantum information? Right? It's you know, the basic building block in quantum information is you know what's called this quantum bit or qubit. Okay, and this is a bit that you know, it doesn't have to be definitely 0 or definitely 1. You know, and you know, and once people hear that, then they say, oh, well, then, you know, that just sounds like a fancy way of saying, well, it's either 0 or it's 1, and you don't know which it is, right? But we know how to deal with that classically, right? We could, you know, we could have a random bit, you know, a bit that has like a 40% chance of being 1 and a 60% chance of being 0, and until you look, you don't know which it is. So you kind of have to think about both possibilities. But then once you look, you know, right? Okay, now that is not a qubit, right? Qubit is more interesting than that, okay? Because what the key thing that quantum mechanics says is that to every possible configuration that a system could be in, like, you know, 0 or 1 in the case of a bit, you have to assign not just a probability, you have to assign a complex number. Okay, these complex numbers are called amplitudes. Okay, they're the basic quantities of quantum mechanics, right? And so for example, a qubit, a quantum bit, might have a square root of a half amplitude to be 0, and it might have a minus square root of a half amplitude to be 1. Okay, or, you know, they could actually be complex numbers, you know, a real plus an imaginary number. Okay, and now when I make a measurement, then these amplitudes convert into probabilities. Okay? And the way they do that is one of the most famous rules in all of physics. It's called the Born rule. Okay, it says that the probability that I see a particular outcome is equal to the square of the absolute value of the amplitude for that outcome. Right. So if I had like an equal superposition, you know, 0 plus 1 divided by the square root of 2, you know, the qubit 0, you know, plus the qubit 1 divided by the square root of 2, okay, and then I measure it, then I'm going to see 0 or 1 equally likely. Okay, but there are other things that I can do besides just measuring the qubit to ask it whether it is 0 or 1. Okay, I can, when the qubit is isolated, then these amplitudes can change in time by rules that are not familiar to our experience. In particular, I can take the list of all the amplitudes of all the possible states, and I can do something to my system, my particles or whatever, that has the effect of doing a linear transformation on that list of amplitudes. Right. So this you could say in some sense what quantum mechanics tells us is that the operating system of the universe is linear algebra. It's matrices and vectors, right? My states are these vectors of amplitudes, these lists of complex numbers. My time evolution, the way the state changes over time while it's isolated, is that I apply what's called a norm-preserving linear transformation, or also called a unitary transformation. Okay, these are like linear transformations, matrices that always map unit vectors to other unit vectors. Right, so they always preserve the length of the vector. Okay, but an example would be a rotation. Right, like I could take a qubit, that is some intermediate state between 0 and 1. Right, somewhere on like the unit circle where here's 0, here's 1, here's -0, here's -1, and I could rotate by a certain fixed angle. Right, or I could reflect about an axis. Okay, these are unitary transformations that I can do, and then I measure, and then measurement is a destructive operation. It sort of collapses me to a single outcome. But now, the key phenomenon that told physicists that, that the world works this way in the first place a century ago. Okay, and that and it is sort of the signature that something quantum is going on, is called interference. Okay, so now if I want to know, let's say, how likely is a particle to hit a certain spot on a screen, right? Then, I have to calculate the amplitude for that thing to happen, right? And then take the squared absolute value, and that gives me the probability. Okay, but the amplitude is a sum of a whole bunch of contributions. Okay, one from every possible path that the photon could have taken, or the particle could have taken, in order to reach, this endpoint, right? And now, if some of those paths that it could have taken make a positive contribution, and others make a negative contribution, then they can interfere destructively and cancel each other out. Meaning, like, the total amplitude will be 0, and then the particle will never be found there at all. Right. Whereas, and here's the even crazier part. If I close off one of the paths, like the famous 2-slit experiment, where there are 2 slits that this particle could go through. If I block one of the 2 slits, well, now I only have a positive contribution or only a negative contribution, depending on which slit I blocked. So now the particle can appear at that endpoint. Okay, so to say it again, by decreasing the number of paths that a particle can take to get somewhere, I can increase the chance that it gets there. Okay, that is something that just forget about all the low level details of physics. Right, that could never happen if the world were described by conventional probability theory. Right, that is sort of the sign that we have. To actually describe what physics is doing, we need different rules of probability. Okay, which is a much more fundamental thing than you might have imagined the laws of physics even talking about at all.
Yeah,
okay? But they do. And so now okay, so now we can come back to the no cloning theorem, since you asked about it. Now a qubit is going to have some state like A times the qubit 0 plus B times the qubit 1, right? Where A and B are amplitudes. Okay, so the state of one qubit is described by a 2-dimensional vector, a list of 2 complex numbers, A and B. Okay, now what would it mean to make a copy of the qubit, right? It would mean that, well, now, what at the other end, I should have 2 qubits that are both in the state A0 plus B1. right? Okay, and now, okay, and the way that in quantum mechanics, the way that we describe sort of two systems that are just sitting there next to each other and that are, separate from each other, that haven't interacted, right? It's a mathematical operation called the tensor product. Okay, but it basically just means, we take like component wise multiplication. So if I have A0 plus B1, for my first qubit times A0 plus B1 for my second qubit, okay, then I can, just like in middle school algebra, I can expand it out and I can say that's an amplitude of A squared for the qubits to both be 0. That's an amplitude of AB for the qubits to be 0 and then 1. It's an amplitude of AB for the qubits to be 1 and then 0. And it's an amplitude of B squared for the qubits to both be 1, right? So now I have a new vector. I want, A squared, AB, and B squared. Okay. But now that we know that, now we've proved the no cloning theorem. Okay. Why have we proved it? Well, because that transformation that we just asked for is a nonlinear transformation. Okay. The amplitudes, A and B, were not replaced by linear functions of A and B. They were replaced by nonlinear functions such as A squared or, B squared. And that is a thing that unitary evolution in quantum mechanics just cannot do. Okay. And so, the way to, there are other ways to prove the no cloning theorem. Okay. But, one way to prove it is really as simple as that.
I see. Now, computational irreducibility. And then also what all of this has to do with Newcomb's paradox.
All right. So, I mean, computational irreducibility is just, a term that Stephen Wolfram uses for, I would say, a basic phenomenon that was, known to many people before Wolfram. He likes to, treat everything as his invention. But, it is, the fact that for many systems that are computationally universal, like we cannot figure out how to predict their behavior faster than just by simulating the whole thing, right?
Mm-hmm.
So there are in some sense science has gotten all as much leverage as it has over the past 400 years because often we can model a system, by something that is simpler than the system itself, right? So, the orbits of, the planets around the sun, the orbit of the moon around the earth, right? Kepler said, these look to me like ellipses, right? And then Newton explained, from a single simple, law of gravitation and from laws of motion, right? He explained why they should look like ellipses, right? And then you can predict, in some cases what the planets are going to be doing millions of years from now, right? Because the system is simple enough. Okay, but there are many other systems. We could take a lava lamp, for example, or the weather, right? Where there is just so much dependence on the fine details of the system state at any one time that if you try to run a prediction to a future time, then your prediction will before long diverge from reality. Okay, this is the famous butterfly effect. Right, that unless the exact state of every particle and can then feed that into your computer, right, then like a small error, whatever small error you make in knowing the current state is going to blow up exponentially over time. Okay, that's the basic phenomenon of chaos. And computational irreducibility, I think it's just the term that Wolfram uses for the analog of chaos in discrete systems like cellular automata.
As you know, on Theories of Everything, we delve into some of the most reality-spiraling concepts from theoretical physics and consciousness to AI and emerging technologies. To stay informed in an ever-evolving landscape, I see The Economist as a wellspring of insightful analysis and in-depth reporting on the various topics we explore here and beyond. The Economist's commitment to rigorous journalism means you get a clear picture of the world's most significant developments, whether it's in scientific innovation or the shifting tectonic plates of global politics. The Economist provides comprehensive coverage that goes beyond the headlines. What sets The Economist apart is their ability to make complex issues accessible and engaging, much like we strive to do in this podcast. If you're passionate about expanding your knowledge and gaining a deeper understanding of the forces that shape our world, then I highly recommend subscribing to The Economist. It's an investment into intellectual growth, one that you won't regret. As a listener of TOE, you get a special 20% off discount. Now you can enjoy The Economist and all it has to offer for less. Head over to their website, www.economist.com/TOE, T-O-E, to get started. Thanks for tuning in, and now back to our explorations of the mysteries of the universe.